So, get started, guys. Thank you. We'll appreciate everyone turning out. A huge turnout for us, so awesome. But also, this is a topic that, in particular for me, is always something that comes up where you have these conversations, and it's, data says this. And for all of us who are like, we want to be more data driven, this is really important. But there's so many times when, without context, you end up wasting a lot of money, whether it's Facebook ads or something else. So it's kind of a near and dear to my heart kind of situation. But so anyway, hi everyone. So I'm Aaron, founder of Promotable. And so what we do is really, we're here to help close that data skills gap. Help everyone, whether you're in marketing or product or finance, be able to learn how to ask the right kinds of questions, be able to, turn that information, your data, into insights. We do that through events like this. We bring in amazing speakers from top companies. And then also we have individual data analytics and Python classes as well. So if you're thinking, hey, I want to dive deeper into data, our classes are 5 hours a week in the evening. So they're 1871 here as well. Go through SQL, Tableau, learn how to tackle problems, tackle data sets, and really make better data-driven decisions. If you're interested in that, feel free to come say hello to me afterwards. If you're not interested, also come say hello to me afterwards. And then other stuff, in 2 weeks, we have the Director of Analytics from Northwestern Medicine. So anyone who's into healthcare analytics and healthcare data, that'll be good. And then the pipeline, we have some folks from Discover and some other places, so definitely look at your emails. With that, let's get started. So I hand it over and make sure the clicker works. Put the website down. It's working. Yeah.
Alright, so as you're probably already aware, I'm going to talk about data-driven mistakes or things to watch out for when you're doing or building data solutions. And I'm not usually tall enough to obstruct views, but if for whatever reason I'm obstructing your view, let me know and I'll try to move around as to the best of my ability. So I'm not going to spend a lot of time on me. Basically, I have a PhD in research methodology with a statistics minor. I have a master's degree in developmental psychology, but I went into the business realm, and I have over 10 years of forecasting experience in corporate. I am currently in a program looking to solve conservation-related problems, which has nothing to do, for the most part, with what I do in my day-to-day. So I am actually a student again with Miami, Ohio University in Brookfield Zoo, and I'm getting a part-time master's degree. And then I just registered to start in the summer for a GIS certificate with Penn State. So as you can see, I'm a lifelong learner. I totally believe in lifelong learning. I have Coursera specializations as well. How many of you have done Coursera? Yeah? Yeah, it can be very, very useful. And then I am the Advanced Analytics Senior Director. I lead Havi's Center of Excellence, Advanced Analytics Center of Excellence. So I pretty much have a team of data scientists and data engineers. I have a product guy, and I also have people with some of the translation skills. So kind of the whole spectrum. I love animals, I love to volunteer, and I absolutely love sports. And as you can see, I am with Havi. How many of you have actually heard of Havi? Okay, so Havi is a global supply chain analytics and logistics company, and we work mostly within the food service industry. And so if you haven't heard about us, or if you don't know that much about us, feel free to ask questions afterwards or look us up online. I'm not going to spend a lot of time talking about the company, okay? All right. So what I'm going to do is I'm going to start out kind of going through what the key concepts are that I want to cover. And then in each slide, I'm going to kind of start to unpack some of these. You'll notice that I'm going to cover some fairly basic concepts, but I'm also going to kind of dig a little bit deeper and get a little bit more technical. So if at any point in time you have a question, please just let me know. Fair enough? All right.
Yes.
Okay. So as you can see, I want to talk about the data solutions life cycle because as we talk about data being data-driven, it means more than obviously just data, right? It's what you do with the data and why you're collecting the data in the first place. So the kind of the circle of life here is defining the problem you're trying to solve, right? That's fairly basic. Specifying the data requirements, which actually can be trickier than what you might think. Data preparation, data exploration. I really want to dive in on the data exploration piece, and I'll show you some examples as we get into that. And then the data analysis and insights. All of that is obviously positioned within the context in which you're working. So I have examples that cover various domains or industries, but if anybody has any specific questions relating to your industry, feel free to ask. I have a fairly eclectic background. So it's kind of awkward because I'm facing you and my back is to the PowerPoint. So I apologize if I turn my back to you occasionally. So as you can see, the very first part is defining the problem. How many of you have had to come up with a business case and determine what is the value proposition of the problem you're trying to solve? Okay. Many of you have, some of you maybe you're more on the data science side where the business experts are doing that. So one of the key things you want to do is whenever you're trying to do something that's data driven to solve a problem, you want to absolutely make sure you engage your domain experts in the very beginning. You should understand what do we already know about the problem, what does the industry tell us, what does academia tell us, and begin to develop hypotheses that you want to then test. Because that'll help you zone in on what the problem is, and it'll help you understand what are the business requirements as well as the data requirements. So it is critically important that you understand the problem and that you work with business domain experts to help you figure that out. I'm not going to go through every word on these slides. You'll have access to this afterwards. So one of the things that you want to do is you want to make sure that as you're brainstorming with the domain experts, I'm assuming most of you are in the data science analytics space. Is that a fair assumption? No? Are you on the business side?
Yes.
Okay. So this is a little bit more biased towards the data science folks, but I'll try to make sure that I keep it a little bit more
I'm
balanced.
just trying to check in on all of you, that's all.
Okay. Perfect.
Learn the language.
Perfect. So make sure when you are brainstorming with the stakeholders that you get a diverse set of views in the room. You absolutely do not want to have everybody you know is going to agree with what you're saying, right? So absolutely have a diverse mindset in the room. Make sure that you review and align on all the assumptions. You're defining everything the same way, and you're all aligned on what the ingoing assumptions are, and I'm going to unpack that a little bit in a few. And then document the business requirements. Most oftentimes, the data scientists are not the ones that are documenting the business requirements. It's somebody on the business side that has some technological background or analytical background. But you should be engaging with them. It should be a collaborative process. If I'm going too fast, please let me know. So specifying the data requirements. When you're thinking about what data do you need, you have to think about many different facets of the data, right? You have to think about the granularity and the cadence. Do you need daily level? Do you need streaming data? How often are decisions made? If you're using a supply chain example, a delivery might go out every third day. So that means that you need to be able to have the data at that level or that interval that you need in order to have that information in time for the decisions to be made. You want to make sure that your data is representative and that you have high fidelity. So what do I mean by that? So obviously you want to make sure that whatever data you're working with, whether it's a random selection or it's selected intentionally, that it represents the holistic problem you're trying to solve. So a lot of times we do convenience sampling, right? Or we work with things that are conveniently available, data sets that are available. But even in random sampling, if your sample isn't large enough, it's not necessarily going to be representative. I know that's a fairly basic concept that most of you probably already understand. So from a fidelity standpoint, a lot of times what we do is we think about trying to test out an intervention, like A/B testing, for example. And we may randomly select or randomly assign to experimental and control But the key point here is whenever you're doing any kind of intervention where you're collecting data that you want to use to solve a problem, you want to make sure that when you are creating a test group, that that group is actually going to do what it is they're supposed to be doing. We call that fidelity, treatment fidelity. So I'll give you an example. If you're going to have a particular campaign or new program that you're doing in your store, let's say you're a store owner, and you have this new customer service program that you're going to train your staff on. If you're doing it with this, let's say you have 10 stores that you manage. If you do it with a handful of stores where you know that the workers are probably not going to do what you want them to do well, that's probably not a good test, right? So you want to make sure that whatever you're measuring is being implemented with fidelity. All right, so I'm going to get a little bit more technical now. When you're thinking about preparing your data, one of the mistakes that people who don't have a lot of experience with statistics or perhaps machine learning is that they don't realize that there are actual things you have to do with your data to make the models make sense, okay? So some people are of the mindset you could just throw all the data into the machine and the machine will figure it out. In some cases that is true. There's a lot of automated, augmented ML these days. You know, Data Robot, Azure ML, lots of different types of platforms that'll do a lot of that data preparation for you. But you still have to know who's doing what, is it happening, and how. Because when you model data and it doesn't meet the assumptions that that model requires, you're going to have invalid results, and therefore you're going to have bad conclusions. So one key thing, this is just kind of, creating z-scores, standardizing your variables if you have continuous variables is always a good thing to do. Always a good thing to do, especially if you're using traditional statistical methods. Because when you have variables that are measured on different scales, that will wreak havoc in your ability to model, in many cases. Identifying and managing anomalies and outliers. Sometimes it's the anomalies that we actually care about. So it's not always that we just want to throw away an anomaly or we want to throw away outliers. Sometimes that's important information. So I would say before you make the decision that you're going to throw it out and impute those values, that you understand, do you need that information? Is that part of the problem you're trying to solve? All right. One caveat, this is from personal experience, one caveat is that we implemented an algorithm called isolation forest using Python. And how many of you have heard of that algorithm, isolation forest? Okay, so it's an anomaly detection algorithm that's based off of random forest. And basically what we did was we were looking at time series data. And we didn't realize it till later in the game. But because of the high seasonality of some of the data, it was treating seasonal data, some instances of the seasonal data as an outlier and throwing it out. So you gotta be very careful when you're using anomaly detection, outlier detection, that you're understanding like what it actually is doing with your data. So don't just let the machine make the decision for you. I already spoke about model assumptions. Make sure that you explore your data and you understand the characteristics of your data and that they align well with whatever model you're trying to use. Some of the most basic examples would be linear regression. Obviously, if you're using linear regression, your predictor variables have to be linearly correlated with a dependent variable, right? So that's just a very basic one. But there's way more statistical assumptions than just linearity. So make sure that you understand the assumptions of the models that you're employing. All right, this is one of my favorite. This is data exploration. I've seen this firsthand, and you'd be surprised at how many people stop at univariate explorations. In other words, they look at a distribution by itself. They don't look at multivariate relationships. This is an example of what I did for my very first research project for my master's program with the zoo in Miami, Ohio. And what my hypothesis was that based on the literature, the birds will prefer the green feeder over the yellow feeder. So I had two feeders. I had one that was a little bit further from the house and had a little bit more tree cover. So what I did was I rotated them. Every time I did a measurement, I'd rotate so that I'd balance out those confounding factors, right? I'd look at time of day, and I try to control for what we're going to talk about later as rival causes. And this was the hypothesis I wanted to test. If I had just looked at a univariate distribution of green and yellow, I would have said, you know what, there really isn't much difference. Color doesn't matter. But I was curious, so I started looking at interaction effects. And what I noticed was color actually does matter. There's an interaction between color and cover. So if you have more tree cover, the birds prefer yellow less. But I would have totally missed that if I didn't start exploring different interactions, different cuts and slices of the data. Now, because this wasn't an a priori hypothesis, I didn't hypothesize this in advance, I was just digging around in the data and exploring, and I happened to find this effect. I would not necessarily conclude that this is a real effect. You would want to replicate the study with that hypothesis and test for that specifically in a validation study. Make sense? All right. Causality and spurious relationships. So I've read some articles online, all this machine learning and AI, and about 5 years ago is when I really started to get into that. I took Andrew Ng's Coursera course, machine learning, and I started getting into the open source stuff and the open source platforms. And I noticed, because my formal training is in statistics and research methodology, I noticed that we got really far away from causality, and there was a pretty heavy focus on prediction. Can you predict? Your predictive models, predictive analytics. There's nothing wrong with predictive analytics, that's great. But I feel we lost sight as an industry on cause and effect. And I've seen in the more recent articles and blogs, we've forgotten about causality. I haven't forgotten about it, but I think a lot of people have. So I want to be very clear that causality requires 3 conditions to be true. Obviously, the 2 variables, x and y, the independent and dependent variable, need to be correlated. If they're not correlated, chances are that there's no causal relationship. X must precede y in time. So if x is the cause of y, x has to happen first and then y. So you need to be able to prove that x came first. And third, and most complicated, is the concept of rival causes. So when you're looking at a correlation between 2 or more variables, you have to be able to rule out rival causes, other plausible explanations for why you found that relationship. And some of those types of examples, you could have a spurious relationship, which means 2 things are correlated, but they have nothing to do with one another, okay? So for example, you launch a promotion in March. You believe that your retail promotion is highly successful because your sales are very high, okay, relative to the prior month. And then, really, what is the true cause? In this case, in this example, most people got their refund checks. So they had more buying power. And that's the true cause of the increase in sales. So that's why the domain experts are dealing with domain experts early on is very important, because they'll kind of know some of these things to watch out for. What are the other rival causes that you might need to control for in your study or in your analysis? So another example is, and this is a criminal justice example, you implement a new neighborhood watch program, and you implement it in December, and you notice that your crime rate went significantly down month over month. So, from the prior month, right? So November versus December. Well, crime goes down when it's cold. So that's a spurious relationship. There really is no relationship between your program and crime. There's a rival cause that explains that relationship. That is really what's happening with the reduction in crime. Make sense so far? How am I doing in terms of level of detail? Do I need to get a little bit more detailed, or am I too detailed? You guys good?
Kind of good.
Okay, all right.
I do have a question. So you mentioned here ruling out rival causes. So one of the things I'm working on right now is, you mentioned refund checks would be a rival cause. In your experience, do you wait and get a new data set to test that out? or do you mock up the data to eliminate that cause and then retest it?
So that's a really good question.
Like, do you have to wait? Or can
So
you
a
go
couple
faster?
things. A couple things that I'm going to get into in the next slide is the best thing to do is look at, obviously you want to look at year over year, because you would assume that March effect of the refund checks is consistent every year.
Shows up every
So you would look at a comp. Comps are a great way to rule out seasonality effects, right? So you look at a comp. That is one thing. Now, if the refund checks are more this year, Trump's, policy where maybe people got more money, let's just say, hypothetically speaking, I don't even know that that's true. But let's say you have a new administration, they changed the tax policy, and you're expecting that people have more buying power this year than they did last year. Then just looking at year over year comp is not enough. So then I would say, try not to launch your campaign in March. So that's where designing your experiment in advance, hypothesizing and dealing with subject matter experts early will help you avoid those kinds of pitfalls. Because you'll say, there's a major confounding or potential confounding event, which is tax returns. And I think it's going to be systematically different this year than it was last year. So I can't just look at a year over year comp. So yeah, you could do, like I said, a couple of things. If you think it's going to be already captured in the year over year, feel free to do it. If you think there's something unique this year, wait till April or May or whatever, because you're putting a lot of money into these campaigns. So you want to make sure that you can get a valid explanation and understand that, yes, it was in fact your campaign that caused the increase in sales and not all these other things. One of the things that really wreaked havoc for us with some of the forecasting that we do is the polar vortex from last year. So my experience in forecasting is that seasonality, if you have seasonality already accounted for in your model, weather doesn't really make a difference unless one of two things happen. It's an extreme event, like a hurricane or polar vortex. That's the first condition. The other condition is if the variability in the weather from day to day is highly volatile. I had the, foresight or whatever to look at that not that long ago, maybe a year or so ago. We didn't just look at weather, we looked at the variability of the weather from day to day. And what I found was that actually was a fairly significant predictor of changes in guest counts and sales. Simply looking at major fluctuations, large standard deviations. So in other words, weather is not in statistical control from a Six Sigma perspective, right? So those are you have to kind of be creative sometimes when you're trying to solve these problems, because it's not always the obvious that you have to look out for. You have to really think about what are some of the potential influences that could impact your program or your whatever it may be that you're trying to do.
Two questions. One is, could you use like econometric data
Absolutely.
to factor your results?
Yeah, and I would say you should if you believe that data, number one, has explanatory value and it can predict. But the other thing too is, and here's where the economic data can get tricky, and I actually talk about this, it might be on the next slide. Not yet, okay, hold that thought right there. One of the watch outs is when you're looking, if you're doing forecasting, if you have to predict something or prescriptive in the future, you can't use data that you only have till current date as part of your model. And with weather, we run into that complication too. So we actually use Weather Source, and Weather Source provides, I think, up to a 15-day forecast. And if that is fairly robust and reliable, then we can use it to predict short-term sales for shipping out case packs, right? But we can't use it for long-term forecasting. And another thing is when you're creating a variable, because a lot of this feature engineering that you're doing is derivations, right? You're creating a new variable based on some product or something that you're doing with the variables you already have. You're taking what you already have and you're creating new variables, okay? One of the caveats with that is, we built some models where guest count was a really good predictor of sales, which makes sense, right? But we don't know what the guest counts are going to be in the future. So now we have to have a forecast going into a forecast. So you have the potential of compounding errors, right? Or compounding errors. So those are the types of things you have to think about in advance, because you can spend a lot of time and a lot of money building something and proving it out in the lab and say, wow, look how predictive my model is. And then when you go to implement it and deploy it in production, in real time, it doesn't work, all right? Because you haven't thoroughly evaluated the constraints that you're up against. Any other, yes?
In case you care, the video recording is stopped because of the sleeping. Like the laptop is on sleep now.
Oh, that thing is?
This thing.
Okay.
So I don't know if you want the recording.
I'm not sure.
I'll go grab Aaron.
Okay, thank you.
Second thing was the election. How does that impact forecasting? That's gonna be hard to factor in.
So I don't know, to be honest with you. I would say my hypothesis would be it probably would only impact that day because people's behaviors are changing that day because people are voting. So their typical behavior and routine for that day is not the same. But I guess it would depend on, like if you're talking about the stock market, obviously that's going to have a major impact on stocks. But in a normal like retail CPG kind of environment, I don't know so much how that would impact those kinds of sales. It's an interesting question. So suppressor effects. Suppressor effects are these sneaky little things that pop up in our models, okay? And sometimes we have the right variables in the model, but we're confused by the results. We're like, why is this a negative coefficient when it should be a positive coefficient? Or when is this a positive coefficient when we expect it to be a negative coefficient? Oftentimes those are suppressor variables that are in your model. Oh, and by the way, I didn't put this in the presentation, but for those of you who are dealing with issues like heteroskedasticity, I don't know how many of you are aware of that term. So you may already know this, but some ways to deal with that are to use hierarchical linear modeling and allow your intercepts and or your slopes to be random. That's one really good way to deal with that. But these are some of the things these sneaky little things that pop up in your analyses. So here's an example of a suppressor effect. You launch an employee training program, and you then compare, you can see the example chart. This is just fake data, by the way. You compare your employees who were in the program to your employees who were not in the program, okay? Post hoc, after the fact. And you say, geez, these are employees that were in this program, they're not doing as well as those that weren't in the program. The program is hurting, right? But you have to factor in the baseline. You have to factor in where they started. And I know this sounds super obvious to a lot of people, but here's why I'm pointing it out. When you design your study, don't make assumptions about what is true and what's not true. Get the facts. Because you might assume that these participants were randomly selected. And then you find out later they were selected because they were low performers. So that's why it's very important to talk to the stakeholders up front and the business folks or whoever it may be that's the domain expert, may not be a business person, and understand the problem that you're trying to solve. And make sure that you have all of the data you need. And in many, many cases, you're going to need baseline information. That's just a given. So some ways, I already mentioned some of this, is to get the baseline, the pre-assessment or the pre-information. Another one is, just use delta. So you can model this data by doing like a pre-post design, like repeated measures ANOVA or an analysis of covariance. But you can also use deltas and just say, what is the change between the pre and post, and just have a single variable in the model and keep it a little bit more simple. There's pros and cons to those approaches. I won't get into that tonight. But these are the things you need to start thinking about. What is the best way to model this data, solve this problem, based on what my problem actually is? The last few slides are probably, hopefully this will be new to you, at least to some extent, and you'll leave here tonight with some new insights and thoughts. So, progress versus perfection. The business does not want you to wait till you have reached perfection for you to give them something. They want progress over perfection, okay? So, if I lead a center of excellence. If I can't show quick time to value, I'm obsolete. right? So what we need to do is we need to make sure that we are able to produce something in a timely manner so that the business can make the decisions that it has to make, all right? And oftentimes, I know because I'm just like many of you, you want to have the best answer. You want to have the most rigorous model. You want every single variable that you can think of. You want to do all these cool things, right? That's great. Do that. But first, give the business something they can work with while you're continually iterating. And on a similar note, make sure you understand what is the value of your effort. There's a concept called diminishing returns that we know very well at Havi. And that is, you can spend a year, $3 million, trying to improve your forecast accuracy. And at the end of the day, the amount in which you improve your forecast accuracy may not really make that much of a difference in terms of your end of the day decision of what you do. And it may not be financially, it may not return that investment. So you have to think about how much money you're spending on your data solution relative to what you're getting out of it. A lot of people say, why wouldn't you use the best model? Well, because it could take me 3 years to build the best model, but I have a good enough model. I have a better than we had before model, right? So those are things that you want to consider. And also assess forecastability. Forecastability is a very important concept. We could spend our lives trying to reduce our forecast error with certain types of series that we're trying to model, right? I can give you a perfect example. We have some restaurants that we forecast for that are in areas that are completely unforecastable. And I say that because we never know what's going to happen. It's very random. It's very, very random. Like a convention center, a restaurant next to a convention center. And you might say, well, why don't you just get that event data and then you can model it and then you can understand it? Well, some of the event data, the geofencing isn't so good. So you get bad information and then your forecast is even worse. Or it may cost a lot of money to buy that data at scale. And at the end of the day, you're probably just going to say, you know what, we're going to handle this one with safety stock. So those are the types of things that you have to think about is how much effort you want to put into solving a problem and what is the return you're going to get.
How do you figure out if the area for the restaurants is forecastable or not?
It depends on their pattern of sales. So if their pattern of sales are, like, as we say, completely out of statistical control, they're all over the place, there's nothing that predicts or explains it, and there's no clear seasonality, there's no clear trend, we cannot necessarily link events or promotions to the sales in a way that is in a systematic fashion, then we say it's not forecastable. Usually we look at the coefficient of variation of the series. That's one way to start to look at it. Other important considerations. What's the time? I'm not quite sure we don't have time here.
6:40.
How much? Okay. All right. So these are really practical, real world things to watch out for. And I'm telling you this because my team built a predictive and prescriptive analytics software, and we had to deal with a lot of these issues, right? Some of them we dealt with up front and we were okay. Some of them bit us in the butt later on because we just didn't know we didn't know what we didn't know, right? And that happens. So the first one is, what can you actually recommend? If you're doing a basket analysis, you're trying to say like what you want to suggest a customer to buy based off of what they already have in their basket. That's just one example, right? If you know that you cannot, it's illegal, or they want to make sure you're not recommending alcohol to a minor. If you know that one of your constraints is you cannot recommend alcohol, even if your model says if they buy X, A, B, or C, or whatever, that there's a high probability if you suggest alcohol, they're going to buy it. You can't do it. So maybe the best predictor or the best relationship, but you can't do it, right? If you have to use interpretable models, now the data science field is getting a lot better at this. You're looking at, I know there's a concept called LIME, and there's other ways where people are starting to look at like local versus global minimums to be able to understand those unexplainable, or I should say, uninterpretable models, those deep neural nets and things of that nature. But in reality, there's going to be situations where you really just can't use a neural network because it's too complicated for your business user, okay? Your translator can't translate it or whatever, or it doesn't make sense to the end user. So sometimes you're stuck with models that are linear regression models, and sometimes the linear regression models are the best models. Law of parsimony, right? So you want to make sure that you're thinking about how that model is being used and who's using it. If you have to explain everything, use something like a linear regression or decision tree. We actually had a constraint when we were building models that the baselines that we were creating had to have smooth, like cosine sine waves, right? Because that reflects the seasonality. So if we used support vector machine, or we used, I'm trying to think of some of the things we used back then, certain things did not give us, gradient boosting regression trees, did not give us a smooth baseline. I don't care how accurate the actual forecast turned out to be, we couldn't use that algorithm, okay? So you have to think about those types of things when you're building your models. Otherwise, you waste a lot of time showing the business something and they say, well, that's not gonna work. Another example is including non-significant promotions for simulation purposes. Sometimes your end user wants to simulate something that isn't significant because they want it, right? So you might find that a particular promotion is not effective. It doesn't do anything to sales or guest counts, right? However, the business feels it's important and they want it in there because they want to simulate that promotion with other factors, right? So you have to consider what the business wants, what your persona wants. A similar example is we were doing, when we created some of the stuff in the early days, we did some interviews with potential people that we wanted to do a POC or a pilot with our software. And we actually had some people, a CFO in particular, who said, I don't even care if your forecast is a little less accurate. I will be happier if I know you accounted for X, Y, and Z. If I know you accounted for weather, even if it doesn't make your model more accurate, even if it makes it slightly less accurate, I'm going to be happier because I know you accounted for it. I can go to sleep at night knowing it's accounted for. So keep that in mind. Do you need to scale your solution? How many of you have scaled solutions, data science, data solutions? Okay, then you know what I'm talking about here. What you build in a sandbox in a Jupyter notebook, all right, or who knows what, is not necessarily going to scale. In a cloud environment, you might need Spark or Databricks or whatever it is that you're using that you're not leveraging in a small experiment on your Jupyter notebook. I will give you a very specific example. We transitioned from SAS to Python about 5 years ago when all this was going on in our company. And we built a model using unobserved component model, okay, in SAS that had really good accuracy. But when we tried to replicate that in R and Python, it blew up. It blew up because Python and R were in beta versions and didn't have all of the parameterization options that you have in SAS. We just couldn't get it to replicate. We spent a lot of time. So make sure that you're prototyping in the same ecosystem environment in which you plan to scale, and consider those costs of scaling, because you might not be able to sell that data model, or you might not be able to get your company to use it if the cost of running those models is greater than any benefit you're going to get from increased sales or what have you. All right. Avoid, and this is, I already talked about this, don't use data that you're not going to have for future reference. So you can't, if you don't have weather data in the future, don't use it in your models. The final thing here is avoid data leakage. What that means is when you're building your models, make sure that the data you train your model on is not confounded with the data you validate your model on. And there's also a concept called exploitation. I did one of those Kaggle contests with the animal shelter thing. And one of the things that happened was the ID of the animal actually determined whether the animal was dead or alive, or euthanized, adopted. And so when we included that variable in the model, it had perfect predictability. But in reality, that was an after-fact thing that that was in the animal's code. We would never have had that data a priori. So consider those types of things. I think this is it. So I know I covered a lot of stuff. I hope that I touched on at least something that was new for you, or something that got you thinking a little bit differently. Are there any other questions?
So this is a little dependent on kind of the time scale for your models. And if your models don't last this long, then feel free to answer accordingly. If you have models that, and you basically have a library of models that are going to be running for 2, 3, 4, 5 years, and they have certain assumptions. So for example, restaurant location populations, and populations change over time. What are your kind of thoughts or guidance on how do you, from a model maintenance standpoint, how can you go back in? You don't want to go back in every time now, rebuild and go back and retest everything over once. So what are your thoughts on kind of managing that maintenance?
That is an excellent question. So the trouble that you get into with that situation is you build a model, you have a history, you say, okay, these are the impacts of these promotions going back 3 years. Now the data changed, right? The census data is different. The percentage of whatever is different in those neighborhoods. So do you go back and restate the history? That's part of the problem. Do you go back and restate the history? Do you go back to the customer and say, all of these things, and the customer could be an internal customer, by the way, all of these things that I calculated and told you these are the effects of all of these different promotions or whatever have all changed. And now we've come to different conclusions. That's one thing that can happen. But to get to how do you manage it, I think the best way to manage that is to look at model drift and data drift. And there are ways that you can do that. To be honest with you, we haven't really gotten there yet. There are ways to do that through things like Microsoft Azure. I would assume there's other platforms that will help you with your data drift and your model drift. But there are things that will monitor. Data Robot will do that. So you basically what you do is it models the drift of your data. Like if your data changes in any kind of significant way, it'll alert you. Or if the departure from your thresholds of accuracy change, it'll alert you. I mean, that's really the bet. I don't know any better. If somebody has a better answer, feel free to provide it. It's a difficult problem.
I have a question. I'm in data engineering side. I've been supporting data scientists for last 7 years.
I love you guys.
But I actually want to ask this because the forum here is all, and I'm not a data scientist by any scale. Over last 10 years, what I've seen is that, you talked about the scale. You do a model testing on a very sample data, and when you do operationalize or productionize, that's where you see the whole problem. In last 4 or 5 years, what have you seen the dependency of data scientists on data engineers? Do you see that data scientists now are smart enough to write those large volume data programs to data munging instead of depending on IT to do that?
So I've seen a shift. I see that the data scientists are becoming way more technical and computer science savvy. And they are able to run Spark jobs and manage Databricks and things like that. The caveat is I don't think they really want to do a lot of that. So I think you'll burn out your data scientists if you ask them and expect them to do that on a regular basis. That shouldn't be like part of their primary day job. I think some of them like to learn it because we're all control freaks in that space. So we want to be able to do everything on our own and not have to rely on anybody if at all possible. But the reality of the situation is we need you.
Yeah, but my another question was, have you seen in market that there's a evolution of new tools which actually makes data scientists more effective?
It is absolutely. So Data Robot is one of them. Now here's the thing that you gotta in Azure ML, we just started using Azure ML and it makes us incredibly more efficient. Here's the caveats there, because we talk about citizen data scientists.
Yes.
I am all about citizen data scientists because I think they can be very good translators and they have all that business domain knowledge. Where you have to be careful is they need to be supervised. I don't mean like supervised learning. I mean supervised by people, right? They need to be supervised so that they're implementing models in an appropriate way. But there's low code, no code options where people can do a lot of that. However, on the ETL side, it's not as mature. That AutoML stuff that we have now is less mature on the ETL side. And so the whole data pipeline, if you go from, getting data acquisition, data integration, and all that, all the way to deploying, when you get to some feature engineering, like transforming the data, all the way through deployment, even into like a Power BI, for example, that is very automated. Can be very automated depending on your platform you're using. The ETL piece, I hear that companies like Trifacta, Informatica, Data IQ, and Databricks now can do a lot of that.
Sorry, I'm not doing my promotion, but Raw Cubes is also doing that.
What is it?
Raw Cubes?
Rock cubes?
Raw Cubes.
Rock cubes.
Yeah.
Okay. Yeah, and I honestly think that just like with data scientists, we're always going to need data engineers. I don't think that skill set's going to go away. We're probably just going to be more efficient.
Yep.
So you'll get more done with fewer people. That's my hypothesis.
Thank you. You had some kind of examples talking about like the best comparable data sets and experimental control and that sort of thing, but in data you often don't get a chance to really engineer a control group like you would in like a lab collecting data experiment. Do you have any kind of pointers on techniques for how you can sort of, with a data set of history, kind of pull out certain groups to use as controls versus?
So yeah, I mean, one way is obviously looking at matched control. So you do cluster analysis. K-means clustering, is a very basic, common one. So you can kind of cluster the data to kind of see what hangs together and then pick that way. Other ways would be, there's a concept called structural equation modeling. How many of you have heard of structural equation modeling? It's like simultaneous regression, right? It's path analysis or path analysis. The difference between the two, if you want to know, I can tell you later. But basically, it's called causal modeling. So hierarchical linear modeling, path analysis, and structural equation modeling all fall into causal modeling. And so that's a really good default to go to when you cannot do experiments. Because a lot of times you can't for ethical reasons. The data is just not, the control groups are just not available. So structural equation models are a really good way to control for and tease out a lot of those confounding variables that you can't control for through a design experiment. Other questions? Anybody have anything you want to add to what I said, or anything that you disagree